Hello. We're going to talk about Newton's first law of motion. This is great because the concept of this is what is at rest stays at rest. What is in motion stays in motion. So the idea behind this is awesome, but it's also confusing because now we're thinking about ideas that occur on Earth here, and this really isn't true. Um, or at least we can't do anything about things that are at rest really staying at rest. So, right now, this pen, the stylus, is actually in motion no matter what I do. Why? Because if we think about it, the Earth is spinning, the Earth is moving throughout space, it's moving in a direction that we don't rightfully know, or people might claim they know. So, this is moving at all times. I mean, it's moving. I'm holding it. I'm moving. This is moving. Everything's moving all the time. Additionally, so even though we think it's at rest, we now have to think about this at rest in a different way. We have to think about it that it takes my energy. I had to eat something in order to have energy to even lift this stylus. Human energy, if we had to do mechanical energy, stuff like that. So energy is being used to move this, even though it's already moving throughout space time. This is all confusing. Maybe if I think about it this way, friction. There's a lot of friction on this planet. There's friction everywhere. There's friction in space, even. It's just very limited. Let's draw a picture to maybe identify what we're talking about here. So here we are on Earth. This is just a Pangea. I don't know. I can't draw. I'm not geographically sound. But anyway, that's just a Pangea of old Earth, let's say. Earth long, long ago. Okay, so Earth long, long ago. Things here, we can pick stuff up. I'll just kind of say we're in Earth, and this is a blown up image of somewhere deep in Earth. And on Earth, there's a table. All right. There is a table. And on this table, I know this is overly complicated, but on this table, there's a ball. And this ball is rolling, and soon it's going to roll off the table. Why? I guess I have to extend this image out a little bit because little Tommy Joe pushed that ball. Okay, little Tommy Joe pushed that ball using human energy, and now that ball is rolling. Now that ball is experiencing a lot of stuff. One of those things is friction. You'll learn that later, but the friction is going to bring it to an earthly rest. Okay? It's going to come back to a rest because it's interacting with its surroundings. Now, I drew Earth for a reason. Okay? We're just talking about what's at rest and what's at motion and why things on Earth don't actually always stay in motion. Well, it's that friction, that interaction. Now let's go to space and let's just take the Earth. Let's just take this planet. This planet is moving. Okay? This planet is moving. I don't know which direction. Let's just put an arrow. It's definitely going somewhere. Okay, and on top of that, there's we got two other planets in between us. All right, we're going to really descale those planets, 1 and 2. And actually, that would be a little smaller. I don't know. Well, let's keep it that way. And then we got this big old sun. Okay. Beautiful. So not only is everything moving one direction, but the Earth is spinning around the sun. It's orbiting the sun. So if I do a big orbit line, but not only is it orbiting the sun, but it's spinning in circles. So I'll do a line like this. So we're Newton's first law is really confusing in that regard, because it's like, okay, well, yes, it's at rest, but it's not because of that. But the earth is in motion and staying in motion. Okay. And the limited friction that the earth is getting, there's these, I'll draw these little dots. You can probably barely see them if you have low quality, but they are atoms in space, right? There are all sorts of atoms in space, and those atoms are friction. It's hitting the atmosphere, right? It's causing it to kind of slow down, in a very microscopic way. Or that's not even a good enough term, but even in a lesser value than you could possibly imagine, and then maybe the thermal dynamics, and I'm just hypothesizing here, maybe the rays coming off the sun do something, I don't even know, but either which way, there is still a little bit of friction. So my craziness about this is that in a perfect environment, and that's how physicists and teachers and professors all do their questioning, in a perfect environment, in an absolutely perfect environment, there is no friction. Okay. And in this perfect environment, so I'll scroll down, we'll call this real. Okay. And now let's go to a perfect environment. Perfect. Pere. Perfect. In a perfect environment, we have little Timmy with, you know, with a ball. And Timmy is going to launch this ball into this hole. So Timmy throws it. Timmy's not that strong, so it hits right here. But in a perfect environment, and I'll actually make this a little crazy. In a perfect environment, we'll do it right there, and that's an equal height. We'll just say that the height is equal to this height. It hits there, no friction, no frick. It hits there, the ball smacks the ground, and because he had some forward momentum, we'll call this eastern bound momentum. Okay. And yes, we are applying gravity on this perfect world. So we'll just say that it's still 9.8, matches Earth. It hits and it rolls into this cavern. Now, typically with some friction, it'll probably go about right here and then start swinging backwards this way. But that's not the case. It's not the case. It'll actually come all the way up. And if it's just enough of a lip right here, maybe it's just a hair lower, it'll actually go over the lip and continue its journey on forever and ever until there's just an oblivious wall, right? Some cliff, right? So this is kind of the 3D environment in which the ball is contained in, right? I don't know how this works in 3D, but there we go. Okay, so it's in that environment and it won't stop until something is massively going to stop it. So no friction. And the funny part about that is if this didn't have friction, it would have a frictionless encounter with this wall right here. And that's a whole nother story. So Newton's first law is really it, it's true, but it's just difficult to compare the two. You'll have test questions like this, but you need to balance your brain out to realize that, unless we satisfy a perfect environment, and you can watch videos on gravity drops without air, friction and all that kind of stuff, and things drop at the same time, and we can talk about that. But first, start off by just separating your head, or just realizing that your everyday events are most likely, I'd say 99.9%, 999 repeating, they're never going to be perfect environments. You're always going to have this statement won't feel like it's ever true. All right. I hope you learned something, and we'll be back for our next video.